GIS Fundamentals, Section 2, Data Models. Data in a GIS represent a simplified view of physical entities. The roads, mountains, accident locations, or other features we wish to identify. Data include information on the spatial location and extent of the entities, and information on their non-spatial properties. Each entity is represented by a spatial feature or cartographic object in the GIS, and so there is an entity-object correspondence. Objects are abstract representations of reality that we store in a spatial database, and they are imperfect representations because we can only record a subset of the characteristics of any entity. A spatial data model may be defined as the objects in a spatial database plus the relationships among them. Coordinates are used to define spatial location and extent of geographic objects. A coordinate most often consists of a pair or triplet of numbers that specify location in relation to a point of origin. The coordinates quantify the distance from the origin when measured along standard distances. Coordinates are usually expressed in one of many standard coordinate systems. The coordinate systems are usually based upon standardized map projections. Typically, attribute data complement coordinate data to define cartographic objects. Attribute data are collected and referenced to each object. Most conceptualizations view the world as a set of layers. These are often referred to as thematic layers. Spatial data in a GIS most often use a Cartesian coordinate system, so named after René Descartes, the system's originator. Cartesian systems define two or three orthogonal, meaning right or 90-degree, axes. Coordinate data may also be specified in a spherical coordinate system. The most common spherical system uses two angles of rotation and a radius distance to specify locations on a modeled Earth surface. The first angle of rotation, the longitude, is measured around the imaginary axis on which the Earth spins, an axis that goes through the North and South poles. Zero is set for a location in England, and the angle is positive eastward and negative westward. The zero longitude, also known as the prime meridian or the Greenwich meridian, was first specified through the Royal Greenwich Observatory in England. A second angle of rotation, measured along lines that intersect both the north and south poles, is used to define a latitude. Latitudes are specified as 0 at the equator, a line encircling the Earth that is always halfway between the north and south poles. Lines of constant longitude are called meridians, and lines of constant latitude are called parallels. Parallels run parallel to each other in an east-west direction around the Earth. The meridians are north-south lines that converge to intersect at the poles. Because the meridians converge, geographic coordinates do not form a Cartesian system. A Cartesian system defines lines on a right-angle planar grid. Geographic coordinates occur on a curved surface, and the longitudinal lines cross at the poles. There are two primary conventions used for specifying the magnitudes of latitude and longitude. The first uses a leading letter, N, S, E, or W, to indicate direction, followed by a number to indicate location. Northern latitudes are preceded by an N, and southern latitudes by an S. Longitudes range from 0 to 180 degrees east or west. Longitudes are positive east, negative west. Signed coordinates are the second common convention for specifying latitude and longitude in a spherical system. Northern latitudes are positive and southern latitudes are negative, and eastern longitudes positive and western longitudes negative. Latitudes vary from negative 90 degrees to 90 degrees, and longitudes vary from negative 180 degrees to 180 degrees. By this convention, the longitudes meet at the maximum and minimum values, so negative 180 degrees equals 180 degrees. Spherical coordinates are most often recorded in a degrees, minutes, seconds, or DMS notation. In DMS, each degree is made up of 60 minutes of arc, and each minute is in turn divided into 60 seconds of arc. Spherical coordinates may also be expressed as decimal degrees. Minutes and seconds are reported as a decimal portion of the degree. Degrees, minutes, seconds may be converted to decimal degrees by decimal degrees equals the degree plus minutes divided by 60 plus seconds divided by 3600. To convert to degrees, minutes, seconds from decimal degrees, the decimal portion is multiplied by 60. And the whole number, and the result of that, the whole number in front of the decimal point equals minutes. Then the remainder after the decimal point is multiplied by 60, and the result of that is the seconds. An ellipsoidal Earth. An ellipsoid is a spherical solid with unequal radii among perpendicular axes. It may be envisioned as being flattened along its axis of revolution. This flattening is quite small and is approximately 1 part in 300. The words spheroid and ellipsoid are often used interchangeably. An ellipsoid is sometimes referred to as an oblate spheroid. Thus, it is less precise, but still correct, to refer to an ellipsoid more generally as a spheroid. The semi-minor axis of an ellipsoid is the smaller axis, which on the Earth would be the axis that the Earth rotates on, that goes from north to south. The semi-major axis would be the larger axis, which would be the equator on the Earth. The best estimates of the Earth's radii are for A, 6,378,137 meters, and for B, 6,356,752 meters. Converting arc to surface distances. We can approximate the surface distance on a circle or sphere by the formula D equals R times O, where D is the approximate ground distance, R is the radius of the circle or sphere, and O is the angle of the arc. Note that the angle is typically specified in radian measure, defined as 2 pi radians per the 360 degrees in a complete circle, or approximately 57 degrees per radian. The great circle distance should be used to estimate the surface distance between 2 points with known latitude and longitude. A great circle is defined as any line resulting from the intersection of a plane passing through the center of a globe. The equator and meridians are great circles, while lines of equal latitude, other than the equator, are not great circles. A great circle distance is the shortest path on the surface of the Earth between 2 points, and long-distance airline routes approximate great circles. Conversion from geographic to three-dimensional Cartesian coordinates. We sometimes must convert between latitude-longitude coordinates and a 3D Cartesian coordinate system. This Cartesian system is aligned with the z-axis through the geographic North Pole and the x and y-axis forming a plane on the equator. Geographic and magnetic north. Magnetic north is the location towards which a compass points. The geographic North Pole is the average northern location of the Earth's axis of rotation. If you were standing on the geographic North Pole with a compass, it would point approximately in the direction of northern Canada, towards magnetic north some 600 kilometers away. The compass will usually point east or west of geographic north, defining an angular distance in the direction to the poles. This angular difference is called the magnetic declination. The specification of spherical coordinate systems is always in reference to the geographic North Pole, not magnetic north. The Earth wobbles or nutates on its axis. This means the axis location varies slightly, within a circle of about 9 meters or 30 feet across, so the apparent North Pole wanders within this circle. The nutation is different than the annual 23.5 degree tilt across the equinoxes. Attribute data and types. Attribute data are used to record the non-spatial characteristics of an entity. Attributes, also called items or variables, may be envisioned as a list of characteristics that describe the features we represent in a GIS. Attributes are often presented in tables and arranged in rows and columns. Each row corresponds to a spatial object, and each column corresponds to an attribute. Attributes can be categorized as nominal, ordinal, or interval ratio attributes. Nominal attributes are variables that provide descriptive information about an object. Examples of nominal attributes are color, vegetation type, city name, parcel owner, or soil type. Ordinal attributes imply a ranking or order by their values. An ordinal attribute may be descriptive, such as high, mid, or low, or it may be numeric. For example, an erosion class may be given a value from 1 to 10. The order reflects only rank and not the scale. Interval ratio attributes are used for numeric items where both rank order and absolute difference in magnitudes are represented. Area, length, weight, height, or depth are a few examples of attributes that are represented by interval ratio variables. Items have a domain, a range of values they may take. Common spatial data models. There are two main conceptualizations used for digital spatial data. The first conceptualization defines discrete objects using a vector data model. Vector data models use discrete elements such as points, lines, and polygons to represent the geometry of real-world entities. Lines and points have coordinate locations, but points have no dimension, and lines have no dimension perpendicular to their direction. Area features may be defined by a closed connected set of lines. The second common conceptualization identifies and represents grid cells for a given region of interest. This conceptualization employs a raster data model. Raster cells are arrayed in a row and column pattern to provide wall-to-wall coverage of a study region. Data models are at times interchangeable in that many phenomena may be represented with either the vector or raster approach. Vector data models. There are three basic types of vector objects: points, lines, and polygons. A point uses a single coordinate pair. The size or dimension of an entity is not important, only its location. Linear features, often referred to as lines or arcs, are represented as lines when using vector data models. Starting points and ending points for a line are sometimes referred to as nodes, while intermediate points in a line are referred to as vertices. Area entities are most often represented by closed polygons. Vector layers sometimes have a many-to-one relationship between geographic features and table rows. Vector layers can have multi-part features because multiple geographic objects may correspond to one row. Polygon inclusions and boundary generalization. Polygon inclusions are areas in a polygon that are different from the rest of the polygon, but still part of the polygon. Inclusions occur because we typically assume an area represented by a polygon is homogeneous. But this assumption may be wrong. A minimum mapping unit is the size of objects we care to record in the data. Boundary generalization is the incomplete representation of boundary locations. Vector topology. Vector data often contain vector topology, enforcing strict connectivity and recording adjacency and planarity. Topological models create an intersection and place a node at each line crossing, recording connectivity and adjacency, and maintaining information on the relationships between and among points, lines, and polygons in spatial data. Planar topology requires that all features occur on a two-dimensional surface. There can be no overlaps among lines or polygons in the same layer. There are additional topological constructs besides planarity that may be specified. For example, polygons may be exhaustive in that there are no gaps, holes, or islands allowed. Line direction may be recorded so that a from and to node are identified in each line. Topological data models often have an advantage of smaller file sizes, largely because coordinate data are recorded once. There are, however, computational costs in defining the topological structure of a vector data layer. Software must determine the connectivity and adjacency information, assign codes, and build topological tables. Also, the data must be very clean, in that all lines must begin and end with a node, and all lines must connect correctly, and all polygons must be closed. Limitations and the extra editing are far outweighed by the gains in efficiency and analytical capabilities provided by topological vector models. Many current vector GIS packages use topological vector models in some form. Raster data models. Raster data models define the world as a regular set of cells in a grid pattern. Raster data models are the natural means to represent continuous spatial features or phenomena. Elevation, precipitation, slope, and pollutant concentration are examples of continuous spatial variables. Raster datasets have a cell dimension, defining the edge length for each square cell. The cell dimension also affects the spatial precision of the dataset, and hence positional accuracy. The cell coordinate is usually defined at a point in the center of the cell. The coordinate applies to the entire area covered by the cell. Positional accuracy is typically expected to be no better than approximately 1/2 the cell size. Raster cell values may be assigned and interpreted in at least 7 different ways. We have described 3. A raster cell is a point physical value, such as elevation, as a statistical value, such as average income, and as discrete data, such as land cover. Raster values may also be used to represent points and lines as the IDs of lines or points that occur closest to the cell center. One common method to assign classes for mixed cells is called winner-take-all. The cell is assigned the class of the largest area type. Raster features and attribute tables. Just as with topological vector data, features in the raster layer may be linked to rows in an attribute table, and these rows may describe the essential non-spatial characteristics of the features. A one-to-one correspondence is rarely used with raster datasets because it often would require an unmanageably large size of attribute table. A many-to-one relationship is usually allowed between raster cells and the attribute table. This substantially reduces the size of the attribute table for most datasets, although it does so at the cost of some spatial ambiguity. An alternative is to maintain the one-to-one relationship, but to index all the raster cells in a contiguous group, thereby reducing the number of rows in the attribute table. This requires software to develop and maintain the indices, and to create them and reconstitute the indexing after spatial operations. A comparison of raster and vector data models. Raster data models exhibit several advantages relative to vector data models. First, raster data models are particularly suitable for representing themes or phenomena that change frequently in space. Raster data structures are generally simpler than vector data models. It is quite easy to code an array structure in most computer languages. Raster data models also facilitate easy overlays. Finally, raster data structures are the most practical method for storing, displaying, and manipulating digital image data, such as aerial photographs and satellite imagery. Vector data models provide some advantages relative to raster data models. First, vector models often lead to more compact data storage. Vector data are a more natural means for representing networks and other connected linear features. Vector data, by their nature, store information on intersections or nodes and the linkages between them, or lines. Traffic volume, speed, timing, and other factors may be associated with lines and intersections to model many kinds of networks. Vector data may be plotted with more visually appealing, continuous lines and rounded edges. Vector data models facilitate the calculation and storage of topological information. Conversion between raster and vector models. Vector to raster conversion involves assigning a cell value for each position occupied by vector features. If the cell size is too large, two or more vector points may fall in the same cell. and either an ambiguous cell identifier is assigned or a more complex numbering and assignment scheme is implemented. Typically, a cell size is chosen such that the diagonal cell dimension is smaller than the distance between the two closest point features. Vector line features in a data layer may also be converted to a raster data model. One simple method assigns a value to a cell if a vector line intersects with any part of the cell. Other assignment rules may be applied. For example, assigning a cell as occupied by a line only when the cell center is near a vector line segment. Near may be defined as some subcell distance. For instance, 1/3 the cell width. The output from vector to raster conversion depends on the algorithm used, even though you use the same input. Linear features represented in a raster environment may be converted to vector lines. Conversion to vector lines typically involves identifying the continuous connected set of grid cells that form the line. Cell centers are typically taken as the locations of vertices along the line. Lines may then be smoothed using a mathematical algorithm to remove the stair-step effect. Other data models. Triangulated irregular networks. A triangulated irregular network, or TIN, is a data model commonly used to represent terrain heights. Typically, the x, y, and z locations for measured points are entered into the TIN data model. These points are distributed in space, and the points may be connected such that the smallest triangle possible spans any 3 adjacent points. The TIN forms a connected network of triangles. Delaunay triangles are created such that the lines from one triangle do not cross the lines of another. Line crossings are avoided by identifying the convergent circle for a set of 3 points. The convergent circle is defined as the circle passing through all 3 points. A triangle is drawn only if the corresponding convergent circle contains no other sampling points. Object data models. The object data model is an alternative for structuring spatial data. The object data model incorporates much of the philosophy of object-oriented programming into a spatial data model. A main goal is to raise the level of abstraction so that the data objects may be conceptualized and addressed in a more natural way. Object models attempt to encapsulate the information and operations, often called methods, into discrete objects. Object models for spatial data often follow a logical model, that is, a user's view of the real objects we portray in a GIS. This model includes all the things of interest and the relationships among them. The logical model is often represented as a box-end line diagram. Most object models define the properties of each object and the relationships among the same and different types of objects. Relationships are an explicit part of the object-oriented design. So rules on object properties, such as pipe materials may be only clay, steel, PVC, or copper, or service lines must connect to main lines, may be explicitly embedded in the database. In other data models, these relationships are often embedded in specific, hard-to-modify computer code, a disadvantage that adds cost and time to modifying a database. Object models can be specified to automatically transfer properties within classes of objects, a capability called inheritance. The object data model has both advantages and disadvantages when compared to traditional topological vector and raster data models. Some geographic entities may be naturally and easily identified as discrete units for particular problems, and so may be naturally amenable to an object-oriented approach. Some proponents claim object models are more easily implemented across a wider range of database software, particularly for complex models. However, object data models are less useful for representing continuously varying features, such as elevation. Finally, we note that there is no widely accepted formal definition of what constitutes an object data model. Three-dimensional data models. Several 3D data models have been proposed with vector-like models, more commonly applied than raster-like models. The latter employ the concept of voxels, or volume elements, essentially cubes of a fixed dimension. Flat or baseline areas have 0 voxels stacked over the surface, with a requisite number of voxels stacked at each raster cell to represent height. Much like 2D vectors, 3D vectors add indexing schemes, with the added complication of a z-coordinate to any element above the base plane of the data layer. Three-dimensional GIS products have become quite mature. For example, the 3D Spatial Analyst and 3D City Engine projects from Esri are full-featured, stable, productive tools supporting start-to-finish workflows. from 2D to 3D data conversion, 3D spatial data ingestion, processing and organizing, and output to project, video, and interactive web services. Three-dimensional GIS processing tools are available from other vendors and as a plugin for QGIS. Multiple models. Historically, hypsography, or terrain heights, was depicted on maps as contour lines. Contours represent lines of equal elevation, typically spaced at fixed elevation intervals across the mapped areas. Because many important analyses are more difficult using contour lines, most digital elevation data are stored using raster or tin models. Data and file structures. Binary and ASCII numbers. All information stored on a computer in a digital format may be represented as a series of zeros and ones. These data are said to be stored in a binary format because each digit may contain one of two values, 0 or 1. Binary numbers are in a base of 2, so each successive column of a number represents a power of 2. Each digit or column in a binary number is called a bit, and 8 columns or bits are called a byte. 1 byte may be used to represent 256 different values. 2 bytes will store up to 65,536 different numbers. ASCII stands for the American Standard Code for Information Interchange. ASCII is a standardized, widespread data format that uses 7 bits, or the numbers 0 through 126, to represent text and other characters. An extended ASCII, or ANSI, American National Standards Institute, scheme, uses these same codes plus an extra binary bit to represent numbers between 127 and 255. Each alphanumeric character corresponds to a specific number between 0 and 255. Binary data are typically used for coordinate information, and ASCII or other codes may be used for attribute data. Pointers and indexes. Data files may be linked by file pointers, indexes, or other structures. A pointer is an address or index that connects one file location to another. Pointers are used to link the set of lines that form each polygon. There is a pointer from each line to the next line, forming a chain that defines the polygon boundary. Shapefiles are a common vector spatial data format that uses an index to link files. Shapefiles represent layers with a cluster of files. Each file has the same base name but a different file name extension. The file name extensions for a shapefile include .shp, .shx, .dbf, and .prj. The first three are all required to represent a vector data layer. These files are connected using indices, numbers that identify connections and groupings for various components. The .shp files contain the coordinates that represent each road, organized by line segments. Segments in the roads.shp file are indexed by pointers in the roads.shx file. The roads.shx file contains indices that point to the segment records in the .shp files. The roads.dbf file also uses an index to point to the combined roads in the .shp and .shx files. A group of segments may be used to form a line and associated with a set of attributes stored in a dbf file. For example, attributes on road name, surface type, or speed limit. By appropriate use of pointers and indices, largely hidden to the user, this group of three shapefiles implements our vector data model. Those four file types are, again, .shp, .shx, .dbf, and .prj. Data compression. Data compression reduces file size while maintaining the information contained in the file. Compression algorithms may be lossless, in that all information is maintained during compression, or lossy, in that some information is lost. Lossy algorithms are most often used with image data, where substantial degradation still leaves a useful image, and are uncommonly applied to thematic spatial data, where any data degradation is typically not tolerated. Data compression is most often applied to discrete raster data. For example, when representing polygon or area information in a raster GIS. There are redundant data elements in raster representations of large homogeneous areas. Run length coding is a common data compression method. This compression technique is based on recording sequential runs of raster cell values. Each run is recorded as the value found in the set of adjacent cells and the run length, or number of cells with the same value. Note that in some instances, run length coding increases the data volume, most often when there are no long runs. There is also some data access cost in run length coding. To locate a cell in run length coding, we must sum along the run length codes to identify a cell position. Quad tree representations are another raster compression method. Quad trees may be thought of as a raster data structure with a variable spatial resolution. Large raster cells that fit entirely into one uniform area are assigned the value corresponding to that area. Successively smaller cells are then fit, halving the cell dimension at each iteration, again fitting the largest cell that will fit in each uniform area. The varying cell size in a quad tree representation requires more sophisticated indexing than simple raster datasets. Pointers are used to link data elements in a tree-like structure, hence the name quad trees. There are many other data compression methods that are commonly applied. LZW is a lossless compression method commonly applied to image and raster datasets. Particularly, GIF images and TIFF formats, JPEG, and wavelet compression algorithms are often applied to reduce the size of spatial data, particularly image or other data, although as implemented, these are lossy algorithms. Generic bit and byte level compression methods may be applied to any files for compression or communications. There is usually some cost in time to the compression and decompression. Raster pyramids. We sometimes intentionally increase the size of our raster datasets without increasing the resolution in a process known as pyramiding. We create pyramids to increase display speeds when viewed at small scales or zoomed out. Long redraw times often hinder use of large datasets, particularly when panning frequently. Pyramiding, in effect, saves subsampled copies of the cells at various resolutions. Note that we say pyramids, in effect, save copies of cells at various resolutions. Sophisticated indexing may be used to point to the cells at the appropriate resolutions. Indexing schemes complicate the simple raster data structure, and the software must be able to navigate the indexing scheme. Common file formats. Common geographic data formats may be placed into three large classes: raster, vector, and attribute. Raster formats may be further split into single-band and multi-band file types. Multi-band raster datasets are most often used to store and distribute image data. while single-band raster datasets are used to store both single-band images and non-spatial data. There is an open source initiative and tool by the name of GDAL, GDAL, for Geospatial Data Abstraction Library, which provides a cross-platform utility to translate among many common vector and raster file formats. Common formats for spatial data include .csv, comma-separated value, is a common ASCII text format used to distribute attribute and often vector information. .dxf, used in Autodesk. .dwg, used in Autodesk. .gdb, .mdb, used in Esri geodatabases. .json, .geojson is an open standard format. .gpkg is a geopackage, which is an open standard format. .tif, .tff are for geotiff, which are open standard formats. .gpx is an open standard format. .img is an image format used in AirDAS. .eoo is an ASCII text file for vector and identifying attribute data used in Esri. .kml is keyhole markup language used in Google. A shapefile consists of .shp, .shx, .dbf, .prj, and others. US Census Tiger format file extensions include tgrxxyy and stfzz. Mapinfo extensions include .mif and .mid. .cdf is a netcdf format. And SDTS is a spatial data transfer standard used by the US government. GIS Fundamentals, Section 2, Data Models, Section Summary. In this section, we have described the main ways of conceptualizing spatial entities, and of representing these entities as spatial features in a computer. We commonly employ two conceptualizations, also called spatial data models: a raster data model and a vector data model. Both models use a combination of coordinates defined in a Cartesian or spherical system and attributes to represent our spatial features. Features are usually segregated by thematic type in layers. Vector data models describe the world as a set of point, line, and area features. Attributes may be associated with each feature. A vector data model splits that world into discrete features and often supports topological relationships. Vector models are most often used to represent features that are considered discrete and are compatible with vector maps, a common output form. Raster data models are based on grid cells and represent the world as a checkerboard, with uniform values within each cell. A raster data model is a natural choice for representing features that vary continuously across space, such as temperature or precipitation. Data may be converted between raster and vector data models. We use data structures and computer codes to represent our conceptualizations in more abstract but computer-compatible forms. These structures may be optimized to reduce storage space and increase access speed, or to enhance processing based on the nature of our spatial data.